Okay, so yeah, so the semester is ended, right? So I guess the goal for this week is to discuss briefly the Cartier curve, which is, I think, very important to get a good understanding of what F-singularities are all about. And next week, we are going to come back and prove some hard results about the regular rings, mostly that they are normal and irrational. And with that, we can be very happy. And because then that would be the last week, we should have to make your presentation, right? So that's briefly the plan. So yeah, I don't know if there are other questions that you may want to discuss. Or, no? So, okay, so far we're in this section 7, which is all about this thing. What is that? Okay, right? So we're studying this, we prove that it exists. Remember, this is the smallest ideal. So what is the data here? Remember that the data here is this thing has to be compatible. So it has to be a C ideal. It has to be an ideal of the pair. Essentially, it has to be an ideal of C that is inside, it's inside R. Well, we need it to be radical, right? That's the only condition. So it's the smallest C ideal, avoiding all minimal primes. Of A. Okay, so we proved that it exists. In fact, there exists an element C, well, that avoids all minimal primes of A, and the way we say that is we define this Q. Q is the union of all the associated primes of A. In this case, A is radical, so we're really just talking about the minimal primes. Let's say P is a minimal prime of R not to A, or it's a minimal prime of A, the equivalent is it is an associated prime of this quotient as an R mod. Okay? And so by prime avoidance, saying that C is not in this union is to say that it avoids being in every single prime. Okay? Of course, if it avoids being in every single prime, it avoids the union. But prime avoidance tells you that these two seemingly different things are the same thing. Okay. So there exists C in here, such that for all R in here, there exists E, which in principle is gigantic, and phi in CE, such that phi sends R to C. Okay. Actually, put in slightly fancier terms, what does this mean? Is that there exists a endomorphism of R, meaning multiplication by something, is multiplication by C. Well, it is C is not a union, so it's not an isomorphism, but it's an endomorphism that so avoiding all minimal primes means that it is essentially generically an isomorphism. Well, generic with respect to A. Sorry, with respect to the generic points of A. Yeah, so geometrically speaking, like you have the full space, you have the closed space cut out by A. It doesn't have to be reducible, it has several components. So there is an open over there, on which this is an isomorphism. That's the point. And so the thing is like, you can have the Frobenius over here, and you can have multiplication by R. Okay, and so the thing is, like, you have this, and what this claims is that for any such R, there will exist a P, making this diagram relative. That's another way to see it. People write it down this way. So you may want to say that this thing is going to be a splitting of this map, but it's not. It's only modulo, this C, common C for all of them. Okay, so we prove that this thing exists, and actually, then you can just take the C to be the sum over the E's. Here, you can be very big. You can start whenever you want. You can start like on anything as large as you want, and then you take P and CE, and what you do is that you multiply P by C, and then you take the image of all these things. Okay, that's an ideal, and that's this test ideal. Okay, so yeah, so actually I was thinking earlier that we proved this, but we didn't quite prove that you can take this guy to be just that. But I'll let you do that as an exercise. It's not too complicated. So another remark that I forgot to mention is not in the notes. Is that all along we could have assumed that A is prime, because actually what you have is the following. So these are the minimal primes. So now this is an exercise in the notes. So what you can say is that if you can prove that these test ideals exist for primes, then you take the sum, and that sum is going to be the test ideal along their intersection. Okay? So in other words, regulate, what is the point? A is the intersection of those primes. That's what it means to be minimal primes. It's a prime decomposition of A. And so tau of an intersection, sort of tau, the sum of the taus, sort of the point, more generally. Okay, so well, there is that. So another remark on the basic properties of this thing is how it localizes. For localization, you have to be a bit careful. But you may want to take the multiplicative closed subset, and you want to localize and see what happens. But here you have to be careful. Actually, the localization only works well if W happens to avoid all these elements. Okay? So if you have a W with this property, then for sure you can localize pretty well. So this is one of the basic properties one has to verify, because when you see that, what it should tell you is that this is a geometric object. It localizes well and fuse well. Okay, so it has to be true. So I'm going to let you do this as an exercise too. Basic. And so there is one more property, which is the so-called restriction theorem. Here. So if you go and look at the literature, this restriction theorem is one of the basic things this object needs to satisfy. So people were defining this object, like to get this thing. Okay. And the property is as follows. So so we still have the same data. So we're going to take a pair, neutral, and we're going to take two ideals that are C ideals, let's say radical C ideals. But actually, one more thing that I forgot that is necessary. Well, I didn't say it over there. But one more thing that is necessary to define the test ideal is that the Cartier pair has to be non-degenerate along A, right? So here we need as usual R comma C non-degenerate along B. And so if it is non-degenerate along B, then it would be non-degenerate along A. Okay? So it's N A. And so I'm doing this because I want to restrict all the data to B. So I'm going to ask, so I'm going to say this. And with this thing in mind, then we have two ideals to consider here. So on one hand, we can take this ideal and we can look at it modulo B. So we can restrict it to B. So we don't know whether or not B is inside here, right? So we don't even know if A is inside here. We don't know that. That's part of the point here. And on the other hand, we have this idea. We can restrict everything to B. So here I should say the C modulo B to X. Yeah, we have said that. Maybe that's the our notation that we had before. So we have these two ideals and they agree. Okay? In other words, if you restrict this test ideal to B, what you get is this test ideal. Okay? So in particular, this is the most common application people have in mind, is that if I have this ideal and I restrict it to A, what I'm gonna get is a test ideal or a C. No, with respect to 0. And actually, we're gonna use this in a sec. So the proof is an exercise. The proof is not super easy, but there is a mind of going to it. Really, it's just taking definitions together, and the only annoyance you will have essentially is to do with minimal prime, make sure that everything that needs to be well defined is well defined in the process. Yeah. Okay, so now finally I can give you a corollary that I really wanted to give you, which is the following. So the finest of centers of purity. So I can do it here. Corollaries the spectrum of centers of purity is finite. Even if this is not a pure. Okay, so remember that these are going to be the prime ideals compatible. So how to say that? these are the prime ideals, right? Like, so they are prime ideals, but they all also have, they're also compatible with the action of the Cartier algebra. But that means like we can take this thing, right? We can take P, we can localize P, and we can take this portion, let me just define it as RP, modulo PRP. And this is a map from the residue field P to kappa P. So I'm going to ask, well, in principle, what this means is that this is different from 0 for some phi Cartier algebra. Okay. So the point is that if you have a prime here, you can take your Cartier algebra, and you can define a Cartier algebra over the residue field. In other words, the residue field is a Cartier algebra. Sorry, it's a Cartier module with respect to C. C acts on the residue field, and what we're asking is that the action is pure, that at least one of those elements is non-zero. Okay, so that C doesn't degenerate at the residue field. You know, and if you have studied the dry geometry, that's a big deal, right? Like dry geometry is about saying, well, a lot of what is happening at residue fields. And so if your data just goes away, then that's bad. Okay, so those are the centers of impurity, and these are finite. That's my plan. So I'd like to prove this. I don't know, any questions with this? So good? So yeah, so here what I'm saying is that if P is such an object, then the residue field kappa P is going to become a Cartier module with respect to C by taking these actions. You know, you can always localize, and since it's compatible, you can further restrict, so you get at something residue field. Sorry, here I meant that makes no sense. I meant here meant to say P I can localize, then I can go modulo that. Sorry. So for the proof goes as follows. Also, I want to appreciate here what's happening, right? Like with the existence of test modules, we were able to guarantee only finiteness, or let's say in this case, centers of purity that are contained in sigma. If you think about it, that's all we could be able to do. But we need like this. Well, we're going to need these more powerful test ideals to get finiteness and centers of purity. So something else was needed. But I don't think no one has like come up with a test module along sub-Cartier module, something like this. So, yeah. But I don't know if it's any interesting, but this one's are, of course. So okay, let's go to the proof. So we're gonna, try to get a contradiction here. So suppose, for the sake of contradiction, that this thing is infinite. What is infinite? But notice two things. First of all, R is a finite, so we know that its dimension is finite, right? This has been our assumption for a long time. And so prime ideals then have only finitely many options for their height. They can have height 0, height 1, height 2, height 3. So what this means is that there will be a height. It's going to have to be positive actually, because there are only finitely many prime ideals of height 0. Right? These are the minimal primes of R, and since R is Noetherian, it is the Scherian, it has only finitely many of those. Okay? So there is a positive number such that let's say the following set me call it S. P, center of purity, such that the height of P is H is infinite. Okay, I'm going to take all of them of the same height. And so the next step is to take Z to be the Zariski closure of S. Right? This is a topological space. Here we have a set, and so I can take its closure. Or I guess we don't need to. I guess we can just be more algebraic and say that, in other words, Z is the closed subset cut out by some radical ideal A, and this radical ideal, well, is the intersection. Right, being radical is equivalent to being an intersection of prime ideals. So it's going to be the intersection of the prime ideals that belong to S. Okay. So let me take this radical ideal. So what properties does it have? Eraser. So it is an intersection of centers of purity. Then what? So that, first of all, well, this is radical, right? Intersection of prime ideals, but also it's intersection of compatible or of a Z ideal, so it is a C ideal. So it belongs here. Moreover, it is non-degenerate, right? Because, well, if you look at its minimal primes, right? Those minimal primes will contain centers of purity. And therefore, if one of them is in the non-pure locus, that center of purity will have to be in the non-pure locus. That's not the case. So it is non-degenerate. Well, what I mean is that the pair is non-degenerate along A. Okay? In other words, the minimal primes are all centers of purity. And this data should give you a test ideal. Right? So we just proved that we can make sense of this thing. It exists. So what else? Yeah, so, and this test ideal is going to have minimal primes. Right, it's going to have P1, P2, P3, Pk, minimal primes. Finally, many of them. And they are centers of purity. But what is the deal? I claim that, I mean, in principle, it can happen that the height of some of them could be H, right? So it may happen. It may happen that one of them belongs to S. I think one cannot rule that out, or one second, I think one could. Let me see how I want to make the argument here. So what definitely cannot happen is that all of them have the same height, because S is infinite. So if they all have the same height, they have to be in S, and actually they have to be the whole list of S. So what's going to happen, right? We have the set S of all these parameters of height H, and every single one of them is going to be contained. So it has to contain at least one of them. So we can separate S in between which one contains this one, which one contains this one, which one contains this. Sorry, are containing this one, and so on. But if some of them have height H, then that is going to be just that point, right? And so what I'm going to say is that this may happen, but we may assume that it doesn't happen. Because if it happened, we can just throw it away. And that would be equivalent to throw away one element of S. And that doesn't affect whether or not S is infinite. Because S is infinite, and if there is one of those parameters that is bothering me, just throw it away. And I still have infinite of one of them. And then I can get a new test ideal for which all of these guys have a smaller height. So let me just put it like this, may assume this. In other words, I can assume that the height of A is less than H. Okay? If not, it's because there is one single prime here that is in S, throw it away. Okay? And well, you cannot just throw away all of them, because then you would be throwing away all of S literally. But it's infinite, so. Okay? So we may assume this. Height of A is strictly less than H. Now, look at this. I claim that this ideal has to be contained in P for all P in S. How do I verify this? What do I need to verify this? For that to be true, I need P to be compatible, which it is, and P must avoid all minimal primes of A. But that's what I just did by guaranteeing this condition. This is the smallest ideal that is compatible and avoids all these primes. But every single element of S satisfies this property, so inside there. This is the key property about this thing. Right? In other words, we can say that it's contained in the intersection of all of them. But what is that thing? It's A. Remember, if everything is looking weird, it's for a reason, because we're looking for a contradiction. So we're not trying to prove something makes sense. We're trying to prove something doesn't make sense. So it should look weird. Okay. So this is equal to A. But what does the restriction theorem tell you? It cannot be. Yeah. Right? But now you apply the restriction theorem. And so if this is the case, then take the tau ARC when extended to R modulo A. Well, since it is inside there, it's 0. But on the other hand, it's a test ideal. But this is non-zero. So you will be proving that 0 equals 0. Okay. So, yeah, that's the application I wanted to give of this test ideal. The proof that these things are finite. They have many more actually, but definitely we don't have time to cover that. It's just hitting to me that the semester is about to end. Okay, so I think with that in place, we can move to the Cartier core map, section 8. Section 8, Cartier core. So what's the point now, right? Like now we know that centers of impurity form a finite set. So, and this seems to be very important. For example, this is a regular. If and only if well, it is pure, for sure. But the centers of impurity has to be made of the minimal primes. So if R is a domain, it can only be 0. So R would be simple here. So, but then we know that in general we're going to have finitely many of them. And so that suggests that there should be a way like to find all of them. And there is indeed a way to do so. Actually, let me say here, like, there's something I want you to notice. Actually, they are constructed like this. You could start with the test ideal. I guess this is sort of another way to argue that they are finite. You could start with the test ideal. Oh, well, sorry. Well, how do you find all centers of impurity of a pair? So first of all, you know that there are trivial ones. But for simplicity, let's assume that R comma C is a pure. I don't, for what I'm saying, I don't think I need it, but I think it's just for simplicity. So, well, first of all, there would be the trivial ones, which are like the generation 0 centers of impurity, which are the minimal primes of R. 0 is always compatible, no matter what. Therefore, its minimal primes are compatible. So you have to put them in there. Okay? So you have 0. So you could call, actually 0 can be thought of as test ideal in a sense. Okay? So you have 0, and then 0 is going to have minimal primes. Let's say k of them. And then you ask, but what else could it be there? If these are the only ones, your ring is a regular and everything is wonderful for your life. But if not, what else is there? Well, you define the test ideal along 0, which is just a test ideal. This is the smallest compatible ideal that avoids disguise. So this would be the first non-trivial piece of information, right? And so the fact that there is something else means that this is proper, that your ring is not irregular. Therefore, it has minimal primes. Right, so this is going to split into a new generation of primes. Just like this. The minimum primes of the test ideal. Right? And then you could say, oh, maybe these are the only centers of impurity. Or not. Right? Then you define a new test ideal, which is a test ideal with respect to that avoids all these things. So you can take the intersection of all the p's and the intersection of all the p primes. Or in other words, this would be the test ideal along this test ideal actually. Okay? And so that would be a new test ideal, and whose minimal primes would be a second generation of centers of impurity that have nothing to do with this. And then you can say, okay, that's the end of the story. No. How do you know? Well, you take a new test ideal, and their minimal primes are going to be the new centers of purity, and you repeat this process until it ends. It has to end, and that's going to give you the whole centers of purity. And they are, you can think of them as the minimal primes of this chain of test ideal. Okay? Actually, if I'm not mistaken, this chain of test ideals may be called Vasilev's chain. Something that appeared in her species, something like that. And then like, you take these minimal primes and they give you layer by layer all centers of purity. Okay? So what I want to do now is to give another way to construct all of them, which is interrelated, but I think it's more elementary. Any questions with that? So yeah, I want you to see how this test ideals stratify your singularities, because it gives you these centers of purity, which is where you should focus your attention when studying F-singularities. Okay. In a sense, I want to make this precise, so not precise, but more. We want to understand this better, and that's the point. So let's start with the definition here. Let me take any ideal of R, and let's start taking simply a P inverse mu. Remember, this is called R. Let's take any one. So first of all, for what we're going to do, I want to define the image of phi with respect to A simply as this. So this is just notation. It looks kind of stupid, but it's going to make things clearer to understand, I think. Okay, this is just a definition. The image of A along phi is this thing. The way to think about it is that it's going to become some sort of as it's called, restriction. So you know that when you're dealing with the deal of extension and restriction, you are going to have this thing, image, and transposition. So the next object, which is less trivial, is going to be the phi transpose. So we're going to define phi. We're going to refer to it as a phi transpose. Okay. It's an object that we have encountered before, I think. But we're going to put it in the center of everything. So we're going to take the elements of R such that when you take a ideal generated by them and you take their image, right? Let me break down what this is. This is just to convince you that you have seen this before. Right? You take that. Another way to think about it is that it's the image of phi times R. And what we want is this equality to be contained in A. Okay? So this, as I wrote it, is an ideal. So in fact, more conceptually, this is the largest or ideal, let's call it B, such that the image of B along phi is inside A. That's all it is. Okay? You look at all ideals of R, that are sent inside A by V. There will be a largest one. That's sort of what I'm taking, that such largest thing exists, because I can give you a formula for what it is. Okay? And yeah, it's that thing. So conceptually, this is the thing, the way to think about it. But if you need a formula to make sure that it exists, it's just that. Okay? So as usual, we need some non-degeneracy thing going on. So C, we say that, we're good. So V is non-degenerate along A if you could say, let me denote by one. So here one is just the ideal one, the ideal generated one. Okay. If one of phi, the image of phi, avoids all minimal primes of A. I'm not saying A is radical. I'm not even saying anything. A is just any ideal in the world. Okay. So properties. So all these properties I'm gonna list here are really basic. So it's really just taking the definition and make sure that all I'm saying is true. I'll let you do that at home. So it's a whole bunch of them. So first of all, these things are geometric construction. They really commute with localization. So if you have a transposition, I should write down something like this. Okay. Commute with localizations. B. So suppose that you have a huge intersection of ideals. So here I have a family A of ideals, just any subset of ideals, right? Any set of ideals, and you transpose that thing. So this is the intersection of AV. Okay. Transposition commute with intersection. That's what I'm saying. As opposed to image. Image commuted sums. So if you have a sum of A in A, and then you take the image, that's the sum of the images. Sorry. So here A is any subset of ideals. Okay, so I just want you to observe the shape, to taste it, you know? Transposition is a multiplicative thing, image is an additive thing. Okay, and so they're going to be sort of dual to one another. And that's the whole business with F-singularities. Okay, with this thing. And I hope you can see that in principle that's very easy to verify. But just do it yourself at home. What else is very basic? The next property, yeah, it's going to tell you that these two constructions are married to one another. So look at this. C. B is inside a phi, if and only if B phi is inside A. You see, with this notation, it sort of becomes very nice. Okay. You want to know if B is in here, all you have to know is if B phi is inside A. So and then when you are doing math, when you do calculations with these things, and you have things like that, that you can move phi freely to different sides of the equation. If it is up in one place, it can go to the other side down. Things like that. Okay? Well, this has the consequence to tell you what is the variety of B phi. Of course, here A and B are any ideals of R. So these are the points for which B is contained in B. Right? The variety of the image of B along phi, not the variety, sorry, the closed set, is a set of points P such that the transposition of P is contained in B. So this has the consequence so this is D, so I guess E is just a consequence. E means that, and this is what I like you to pay attention to. This is what we want. P to the phi is different from R, is a proper ideal, if and only if phi is not contained. So if P avoids the image of phi, then this happens. And so this look at this, right? This has to tell you about F purity. So F purity, which is this is the way we have been understanding it, now has this counterpart in terms of transpositions. Okay? So I guess one more consequence is this would be F. Then the non-F pure locus of this thing, so this was the non-F pure locus. Actually, we may want to give this a name. I don't know, maybe I call it Z. Z of R comma phi. So what this says is that now this is going to be given by the prime ideals such that its transposition with respect to phi is R. Okay? That's the first punchline. Transpositions detect non-F purity or F purity. Okay? If you want to know whether or not P is in the F pure locus, all you have to do is to compute this transposition and see whether or not it's R. Okay? So I hope you can see that now we're trying to have a change of paradigm in a sense. We're trying to look at things differently now in terms of this course. What else? There is that. I guess we want to say G. G is kind of weird, but it's very useful. So we have an inclusion. This inclusion is kind of trivial. So I'm going to take R and I'm going to intersect it with this thing. Okay. This is just this thing. When I want you to prove this, you want to take the image. This is the image of phi. This ideal here. So this is an equality. If and only if, and this is the point I want to make with this exercise. I want you to have it there because it's a very good trick to know whether or not A is going to be non-degenerate. That's how you do it. If and only if phi is non-degenerate along A. Okay. So, for example, I want you to use that to prove that if phi is not degenerate along A, then you can prove that A is always contained inside inside its transposition. So whenever you have a non-degeneracy equation, you can think of the transposition as some sort of closure. Jeez. Sorry. I guess no one is on Zoom. But still. Okay. When the situation is non-degenerate, this ideal becomes larger. Sort of as a closure type of operation. Okay. This thing commute with the product of the Cartier algebra. Okay. And finally, you can think of the set of phi ideals as a set of ideals of R. Well, the definition we had before is this. This was the definition. There is nothing new here. Just notation. This is the image of A along phi has to be contained there. But now it's gonna be what? It's gonna be the set of ideals such that A is contained in A to the phi. And therefore, when there is a non-degeneracy condition, what you're going to have here is inequality automatically. Okay. Phi ideals can be understood in terms of transpositions. Are those ideals A that lives inside? No, sorry. What? Yeah, like that. Like that, and no, wait. Then there's a typo here. So be non-degenerate. Yeah, these two things are equivalent. So I think then what sorry. I think I meant to say this. I'm sorry. Yeah, like this. Sorry. So yeah, the phi ideals are those for which, sorry, this is going to look like this type of closure. But then if there's no degeneracy, then they just match. Okay. Actually, when they match, in general, they're called fixed ideals of the action of phi, or more generally, the action of the Cartier algebra if we intersect over all actions. And so that's something that is, I think there is some interest in that, but I don't understand it too much. I don't know what's the deal with that. For example, I think it's an open problem to prove that the set of fixed ideals is finite. So when A equals a phi, A is a fixed ideal. Okay. So non-degenerate C ideals are fixed, but there could be more. I think there's a conjecture that they're finite. Conjecture, fixed ideals, finite sets. But I think it's open. Maybe some weird type of new test ideology, it's necessary to do that. So I've heard people asking questions. I don't know what they have in mind, or what could be an application, but it's certainly true that fixed ideals show up sometimes in mysterious ways. Of course, this is only interesting if you are not working with the pure things. Okay. If you have pure things, everything coincides, everything is non-degenerate. So fixed ideals and C ideals are the same thing. Okay. We know that non-degenerate, right? That's what we proved. Non-degenerate C-ideals are finite, right? The fixed ideal is a larger class. It's a larger class. Okay. Try to prove that they're finite. I think that could be, published. Sure. I wonder if it requires really a new type of test ideal, but I don't know. I don't know much about it, to be honest. Okay. So that finishes all this basic properties. Okay. So remark I wanted to make is that when studying these compatible ideals, we can always sort of just reduce the case in which we play with one single key, right? Because we always have this. Right? A C ideal is something that is compatible with all elements P in that C. There's nothing to go into it. So somehow I also want to make one more remark here. That is, it's kind of trivial. So, and so this is a lattice, right? That we've been studying quite a bit, and we learned that what really matters about this lattice are the prime ideals, because any other ideal in there is an intersection of those or sums and so on. Prime ideals are really the important objects. So let me define two things. I'm going to define the Cartier spectrum of this thing. I'm just going to get this thing. I'm just introducing some notation that's going to make that easier. And inside here, there is what we have defined already. This Cartier, this Schwitt spectrum, which are the things in here that are centers of continuity, right? So P in a spectrum of R, such that I'm just going to say kappa P, comma, the Cartier algebra obtained by localizing at P and then killing P, okay, is here. Which is kind of a stupid thing to say, right? But we're playing with a field. So that Cartier algebra is either 0 or the whole thing, right? But what we're saying is like, this object just doesn't collapse to 0, which can happen. Well, in higher degrees, right? In 0 degree, it won't. Okay, so okay, these are objects we have defined before, but now the key observation is to give them a topology. It's just to treat them as topological spaces. So give them the subspace topology, because it's a risky topology. Right? They live inside the spectrum, so they can have a topology. So then we're going to define our objects. So what are the closed subsets in C-spec R? So they're going to look like, well, let me say, they're going to look like For example, you take this, and by definition, you have to intersect with a closed subset of this vectional part. Right, that's what subspace topology. You just take all the closed subset and you intersect them with that subspace. So you get this, and we're gonna call this a closed subset in here, defined by A. But just to make sure that we're talking about something in here, I'm gonna put a C here. Okay, and likewise, we're gonna have a spec. C. A. And just to tell them apart, there's gonna be a circ here. And I want to tell you why about this circ. And the reason is something that probably you have noticed before. Grab it. I think I can write it down here. So the reason is that, look at this. In principle, we have all these prime ideals that are compatible with C. But you can prove, well, it's not, well, it's just true at this point. It should be a very simple observation. That either a prime ideal that is compatible with C is either a center of purity or else, right? And this is a disjoint union, belongs to the singular locus. Those are the non-pure locus that we just defined before. This closed subset here is defined by sigma, and sigma is compatible. So this object here is closed inside here. Okay? If you have a prime ideal that is compatible with C, it's either a center of purity for which there are finitely many of them, or it contains sigma. That's what this tells you. Or is the whole variety of sigma, right? This Z, the non-pure locus, is the variety of sigma, which in principle can be huge. It doesn't have to be infinite. It doesn't have to. But it's in principle huge, right? It's a whole subvariety, or not variety, close subset, right? That you have infinite many points, infinitely many maximum ideas, right? So you can see how the world here is split in between these two things. So the point here is that this spec is an open subset in there. It is literally the intersection of this with the F pure locus. Okay? So yeah, sorry, I'm just making like trivial observation, but this are conceptually important. Understand what's happening. So in other words, let me just write it down like this spec or comma C, when you take this and you intersect it, let me call it the F pure locus. Okay? Pure locus. And so this is an open. This here is an open of C spec. Okay? Now we have topology and we're going to have an open inside here. Okay? Any questions so far with this? I'm getting hungry now. So. Okay, and so let me make a few more remarks. But probably you know by now, probably we have used this before, but let me add to that a logical component here. So, proposition, / exercise. There is really nothing going to it, it's just pure definitions. So, yeah, for this proposition, I'm going to take a pair. I'm going to take any ideal. And I'm going to take a multiplicatively closed subset. They're the usual things. So the first thing is that you're going to have a quotient map, R modulo A, right? So this is in principle the map corresponding to the closed embedding of VA inside the spec R, right? And so you know that extensions of ideals, let me put it like this. Probably you know this by the name of the isomorphism theorems or something. Right? The ideals of R modulo A are in one-to-one correspondence with the ideals of R that contains A. Right? How is that called? The Schneider isomorphism theorem or something like that. And this is just extension of ideals, right? You take B, you extend it. Okay. So the same is going to be true for compatible ideals. So you have here R comma C, that you're going to have C comma. Does that make sense? All I'm saying is that this isomorphism theorem extends to C ideals. There's no surprise there. Okay, but who cares? The point is that then, just as in basic commutative algebra, you're gonna get out of this, it just restricts to isomorphism, to homomorphisms. Okay, so you have this closed. It's gonna be a homeomorphism. So this is a little sanity check that we're doing things correctly. Okay. Right, you remember this from, if you remove the C, this is just to say that V of A is homomorphic to the spectrum of R modulo A. And the homomorphism is just given by extension and contraction. Okay. And of course, also this. It's also a homomorphism. Okay. So these closed subsets, right? One is proposing for the Savinsky topology of spec. It's really made out of other specs. Okay. And likewise for localization. So where is it? So the other part of the exercise is that if you go and look at localization, let me call it lambda. So then you know that we have the lattices of ideals here, and you can get an ideal here. So here you can do extension, right? Extension is that you take an ideal here and you localize it, but that's the same thing as A underscore. So this is not an isomorphism, right? It's not even an isomorphism for ideals, but it is a homomorphism of lattices. So all I'm saying is that well, you know already that localization commute with intersections and sums and so on. All that basic commutative algebra extends here, and it's going to give you the following homomorphisms. And I think we can finish with that. It's almost lunchtime. And so this thing is going to tell you that if you look at the compatible prime ideals, so this is going to be a homomorphic spec. Okay. This is how this construction works with respect to the localization. Is what you expect, right? From basic commutative algebra, I would say that all that basic stuff extends. And moreover, centers of purity corresponds to centers of purity. So over here, you're going to have the P in spec such that P doesn't intersect W, and that's going to map homeomorphically to spec. So in other words, centers of purity commute reasonably well with localization. So I guess probably you have been using this already to do several exercises. Maybe I have done it already in the class. But I think the part I want to emphasize really is that when I write this down, I'm talking about topological spaces. Okay? It's not just a projection. That's fine. That's homeo. Same here. So yeah, so I think we can stop here. I can tell you very quick what we're going to do on Thursday. On Thursday, now we're going to get serious and we're going to find the Cartier core map. And we're going to use these topological considerations to observe that it's just a topological thing going on. Okay. So see you on Thursday.